All right. Well, it's nice to have you all around. Today's session is not going to be very long. We're going to talk about exponential functions, okay? Exponential functions are power functions, okay? But they are not additive. They are more like they are multiplicative. That is why we call them exponential functions. And also, we would have talked about logarithmic functions, but we're not emphasizing them here, except that we're going to essentially apply them by introducing essentially how to look for a log. I believe many of you know how to look for a log on your laptop, on your calculators. And these days, your telephones have calculators. And we're just going to apply, look at a problem that you have to solve by using the logarithmic calculation. Okay, so let me just put up an example of an exponential function. Okay, now exponential functions are usually used to solve problems of growth. Okay, for example, if you have f of x, that is function of x, so it's equal to 2x squared plus 4x to the power 3. All right. This is not an exponential function. Okay, this is a polynomial function. You can see it is additive. 2x to the power 2 plus 4x to the power 3. Okay, this is a polynomial function. Suppose you have f of x is equal to, say, 4x so 4 times e to the power x. Then this is, just a minute.
I'm sorry, I'm a little lost. 4e, where did we get the e from?
Sorry, my wife was calling on the phone. If I don't answer, then I have a lot of trouble. Okay.
That's funny.
Well, I think we all know the deal.
We sure do.
Okay. So, so somebody says, where do you get the E? Okay. E is an exponential symbol. Okay. It's an exponential symbol. E, mathematically, is equal to 2.8 whatever. Okay. It's a fixed number. Okay. But you raise to the power x. Okay. So this is what is called an exponential function. It's an exponent. E is called an exponent. Okay, it has a fixed value. It's like pi. Okay, who knows the value of pi? Who remembers the value of pi?
Isn't it like 3 point something, 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 something?
That's correct. Okay. Okay, E is 2.718, 2.718. Okay, and pi is 3.141414. So these are mathematical numbers that are determined by, I will say, a function which we are not equipped in this class. I mean, I can do it, but it doesn't make sense trying to explain to you the mathematical function. Okay. For example, pi comes out of the relationships of circles and lines. And that is how we come to know that pi is equal to 3.14, whatever. Same thing with E. Okay. Okay. But that's not supposed to be our concern. What we are going to do is we're going to solve problems that have E and other kinds of power functions. For example, suppose that f of x is, say, 4 times 1 point, say, one plus k, not 1.k, 1 plus k, and where k is a known number, to the power n, okay, or to the power x. This is also an exponential function, okay? So n could be number of years, number of minutes, okay, number of times, and k is a known number, okay? We're good. In that case, we'll give you k, all right? So those two last functions are called exponential functions, while the first function is a polynomial function. Okay, you can see it's additive, while the other two functions are more like they're multiplicative, or they are raised to some power of the variable. Okay, the variable here is x, and the variable here is n. All right, so let's look at some examples. We're not going to be talking about polynomials, which we already talked about. We're just going to talk about exponential functions. Okay. Now, a good example of polynomial function is a growth function. Okay. Functions that grow. Let us say that, say, population. Okay. The population of say, a community begins from, say, 500. Let us say a small community of 500 today, okay? And that community is gonna grow by 5%, 5% being 1.05, going to grow by 5%. For 10 years, okay? So we're going to say 1.05 to the power 10, all right? For 10 years. So that's an n. So what will be the population in 10 years? So the population in 10 years then will be 1.05 to the power 10 times 500. Okay. So what is 1.05 to the power 10? 1.05, you can do that on your calculator. 1.05 to the power 10 is 1.6288. So the population will be 500 times 1.6889 1.628889. Okay. Now,
That equals 814.447.
that's correct. 814.447. Okay. All right. So now you would ask me, if it's that simple, why are we going through it? Now, we're going to make it a little bit more interesting, but essentially you have a straightforward function. You're told that population will grow by 5%, which is 1.05 to the power 10. So in 10 years, the population will be about 814, between 814 and 815. Because since we're talking about population here, you don't have 44% of a person or what have you, or a fraction of a person. So you're going to be looking at approximately 815 or 814. Okay. Now, when we look at a function like this, we simply say that this is a function of, say, discrete growth. That is to say, the population does not grow until the end of 1 year. It's a discrete growth, okay? Population does not grow until the end of 1 year. So it's like 1 year, 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, and that's how it grows. It does not grow continuously as such. We have another kind of exponential function, like where we have like growth by the millisecond or whatever. This is why you have the exponent type of function with the e. You have continuous growth, so the population, say y of x grows continuously, is equal to, say, 500. Like if you have money, and money is, the interest is compounded every minute. Okay, so times e to the power 0.024 t. And see, you have it as an exponent. Okay, have it as an exponent with an e. Okay, the exponential sign. All right, so in that case, we simply take e to the power 0.024. Okay, let t be equal to, say, 40. Okay. Okay, let t be equal to 40, and to be 40 years. We can use that. Okay. And so in that case, y will be equal to 500 times e to the power 0.025 times 40.
Before you move on, why did it change to 0.25?
0.025. I'm going
And the other equation, you put 0.024.
Oh, okay, sorry.
Okay.
Thank you for that clarification. It's a typo. 0.024 times 40. Okay. All right. So what is 0.024 times 40?
.96.
0.96. Okay, so y becomes 500 times e to the power 0.96. Okay, so we'll find e to the power 0.96. What is it?
No. Moi, je la mettais dans ma microwave là, sorti pour pouvoir. Oh, okay. No?
Somebody's not muted.
Please mute yourself so we don't hear all the background conversations.
Okay, I'm trying to move myself.
To be equal to
Okay, I will see. Okay, I will get.
500 times 617
Nuchilana, you're not muted.
117. So what is that?
It's 1,305.85.
Okay.
Excuse me, could you mute yourself, please? Can you mute yourself, please?
All right. So this is how to solve this kind of problem. But where the problem becomes interesting is when we ask the question for you to find the variable exponential value. Okay. For example, how long would it take for the population to be 2,000? Okay. This is where we now talk about logs. And like I said, I would love to go and talk about the methods and the theories of logs, but we're not going to demand that in this class. Okay, but you know how to find logs, and so we're going to try to find logs. Where we ask the question, for example, you deposit, let's say we deposit $400. Okay. Let's make it some attractive amount. $4,000 is good money. Okay. We deposit $4,000. Or there are 4,000 trees in a forest. And your $4,000 will earn interest at 3% per year. How long would it take to become 7,000? Okay. So interest call it INT, is equal to, say, 3%. Okay, 3% interest. So how long would it take for it to be how long? Pardon me, this Blackboard annotation. Okay, how long? To grow. To say 1,500.
So the question is how long it would take the interest amount to grow to 1,500?
No,
or
how
in
long would
addition-
the deposit, how long would the original deposit grow to
To-
1,500?
Okay.
Okay, the money is going to be growing at 3%. If somebody's going to add 3% on it. Now, we're going to solve the problem in two ways, where we're going to use the logarithmic process, okay? We're going to solve it like discrete growth, which means it's at the end of 1 year, somebody will add 3% to your money, okay? As opposed to if the money is compounded continuously, like every minute, then we use the E function, all right? So we know what the numbers are. We're going to deposit $4,000. The interest is 3% per year. How long would it grow? How long would it take to grow to 1,500? So how long will the deposit of $4,000 grow to 1,500? Okay.
But isn't that impossible, Professor? It's not going to
Actually,
grow.
yeah, your money is growing. I mean, if somebody is putting 3% on your money every at the end of every year, it will grow. It will become more than 400 in 10 years. It will become, it will become more than 4,000 in 10 years. It will become more than 4,000 in 12 years.
But your initial deposit is more than the goal that you're trying to reach of 1,500.
Oh, I'm
So then-
sorry. Oh, well, that means it grows negatively. I'm sorry. Let's make it 15,000.
Sorry, I was a little confused.
That's why it was. That's what my question was. Do you want the interest to grow to 15,000 alone, or in addition to the
No.
initial?
He might have meant 15,000 instead of 1,500.
Yes, I meant 15,000 because what was in my mind originally was 400. Okay.
Okay, thanks, Professor.
Okay. So how long would it take to grow to $15,000? Okay. And so this time around, we are assuming discrete growth. Okay. And I'm going to use one of the homework assignment problems to illustrate the exponential with the E function. All right. So, and again, thank you for calling me back. I'm going astray. Okay, so well, we deposit 4,000 and we want to know how long it will grow, how long it will take to grow to 15,000. So we put in here the 15,000, which is our f of x, because now we know what it will grow to. Okay, we know what it will grow to. And so 15,000 will then be the 4,000. And this is discrete growth times 1.03 to the power n. Remember the last time we put into the power 10, where n is equal to 10. But this time we don't know what n is, but we know how much we want to the money to grow to. We know here this is f of x this is our f of x here. Excuse me, I'm getting into some problem here. Okay. Initial amount. This is the initial amount times 1 plus the growth amount, the growth rate, g, to the power n. Okay. And we know that we are looking at 15,000. Equal to initial amount, which is 4,000, times 1.03 to the power n. Okay. So you can see 0.03 is the growth amount G, 4,000 is the initial investment I, and n is the number of years it will take to grow to 15,000. So we don't know what n is. So we're going to solve for n. Okay, we're going to solve for n. And so the best way to solve this kind of problem is to divide both sides by 4,000, because the 4,000 is multiplicative to 1.03 to the power n.
Okay, so that would be 3.75.
Okay, so we have 3 thank you very much for helping.
Wait, I'm sorry. How did we get to 3.75? I missed that. I'm sorry.
We did
Okay.
15,000 divided
Okay.
by 4,000.
4. Okay, so
Okay,
let's let's make it easier for everybody to understand. Okay. So the best way to start solving is to take 15,000. Let's all be patient. Divided by 4,000. Is equal to 1.03 to the power n. All right? Because we divided both sides by 4,000. So if you divide 4,000 into 4,000, you get 1. Am I correct? Hello?
Yes.
Okay. So if
Yes.
you divide 15,000 by 4,000, then we get our good friends 3.75. So 3.75 is equal to 1.03 to the power n. Okay. So then how do we resolve this power function on both sides? Because this is the multiplicative power function to the power n. So how do you now reduce the equation to a linear problem? This is where we have an issue here. We have to reduce this equation to a linear problem because we are raising the other side to a power. We are not multiplying by n, because if you are multiplying by n, all you have to do is to divide both sides by 1.03 and you have your answer. But we are not multiplying by n, we are raising to the power n. Okay. Now, this requires us, or this, would have been maybe more interesting for those who are mathematically inclined to go and find out exactly why we use a log. Okay. If you want that, maybe we'll talk about it next time, why we use these logs. Okay. But if you have this kind of power function, what you then do is you realize that if you take a function that is raised to a power and do the log of that function, then the solution will be to say that n times the log of 1.03. I'm just giving you a mechanical solution, is equal to, now you have to do the log of both sides. Okay. The log of 3.75. So you find the log of 3.75 and the log of 1.03. Okay, that is in your calculators. So in that case, you now reduce the problem to a linear function. Okay, and so n will be the log of 3.75 divided by the log of 1.03. Okay. You are not talking about the log of the division 3.75 over 1.03. No, that's not what you're talking about. It has to be the log of the upper number. And so let's make it straight, let's make it clear to everybody. N will be the log of 3.75 divided by the log of 1.03. All right, 3.75 at 1.03. Okay, let me make it very clear. We are not talking about this is what some students do, and this is what I did way back then when I was trying to learn this. These are two different things.
So I looked it up and the log of 3.75 is is 0.5740.
Okay, all right. So hold on to that thought. It's a great thought.
Okay.
See what I put on the side is crossed out. We're not talking about the log of 3.75 over 1.03. No, that is wrong. This is the correct thing. The log of 3.75 calculated separately, and the log of 1.03 calculated separately. So what is the log of 3.75?
Is 0.5740.
Okay. 0.75
0.57.
or 0.57.
Mm-hmm.
Okay. Give me a minute.
Sure. I'm gonna mute myself.
Okay. 0.57.
5740. And then the log.
Okay, so let's take 574.
Okay.
And the log of 1.03 is?
Is 0.01283. So
128.
128, yeah.
Okay, let's take 128. And what does that give us?
It gives us 44.738. So if this is correct, it would take 44 years.
Yes.
44 and 3/4 years for the interest to be 15,000.
For the original deposit to amount to 15,000 for your money.
Correct. Not the interest. So the original deposit to equal 15,000.
Yes.
Okay. Thank you.
Okay. So if you deposit $4,000 and that $4,000 is compounded every year, at the end of every year, it will take 44 years for your $4,000 to grow to 15,000 if you earn 3% interest on it. I mean, if you earn 10% interest on it, that will be a shorter period of time. So if you earn 3% interest on it, yes, it will take 44 years. All right? All right. Now,
I have a quick question.
sure.
Could you explain what the log of a number means? Because I never heard that in my life.
No. If you did high school, you probably heard of it because you forgot. If you did high school, all I can say is that you forgot. And believe you me, if you did high school many years ago, you will forget.
Okay, maybe,
Okay.
but
okay. The the log of a number. So let us say you take a number like 7, and you raise it to the power 3, right?
okay.
Okay. So what it simply means is that if you take the result and take the log of it, then say if you take 3 log 7, then you will get the same thing as you get by taking 7 and raise it to the power 3. That's what it is. Okay. But if you want to know what the log of a number is, I think the best thing will be for us to make this a lecture so that we understand exactly what logs mean. I'm not going to give you a quick explanation here, so I mean you get confused, okay? But the log of a number is there in your calculator. But since you are raising the question, I'm going to make it a lecture next week.
Okay. Okay, thank you.
But we're not going to be using it in this class. That is, we're not going to be doing the theory of logs in this class. Okay? That's going to be a little time consuming.
My suggestion is you just look it up on Google.
Yes.
Yeah, I'll figure it out. I'll figure it out. Thank you.
Okay.
Literally just type in log of and then put the number in.
Oh yeah, I know how to get the answer. I just don't know what it means. I mean, I get it. Like, I know how to put it in a calculator or whatever, but okay, I'll figure it out. Thanks.
And like I say, you know, I mean, you can look it up on Google, and that you know, it's something that we can also, you know, I mean, it's you know, what do you call it? 9th grade algebra, so it's not like a big deal. It's just that, you know, spending time to explain it in a class when we're not going to really be using it, we're not going to be questioned on it.
Not a good use of our time.
Yeah, it's not a good use of your time here. So this is why I'm not dealing with it. Otherwise, it's easy to explain. We can go through some theoretical explanations.
Okay, no problem.
Okay, so now see, like I said, this is a discrete thing, a discrete growth in the sense that if your money was compounded at the end of every 6 months, for example, okay, then it will grow faster. It will take fewer number of years for it to grow from 4,000 to 15,000. If you compounded it every 3 months, it will also grow faster, okay? And we're not saying that if it is compounded, if your money is compounded every 6 months, then you will get only half of 3%. If your money is compounded every 3 months, then you're going to get 1/4 of 3%. Nevertheless, it will take a shorter time. It will take less than 44 years for your money to grow to 15,000, okay? Because your interest is added and then compounded much more frequently, okay? And we're going to get to that. So next week, we're going to go into really financial mathematics of finance. We're going to get into that, and you're going to see more of what I'm talking about. But let's take one of your homework problems that is based on exponential functions.
Now that you're bringing up the homework problem, I have a question.
Sure.
For number 2 on the homework, where you say A of t equals 115 times 1.025 t, okay. Is there supposed to be a plus sign in between?
Let me pull up. Let me share my screen.
I unfortunately I have to like go around 7 o'clock, so I just that was one question before I go.
Okay, and I'm going to make it easy for you to leave in the next 7 minutes.
Thank you, appreciate it.
All right, so which one are you talking about?
So number 2, if you scroll up, it says the following exercises consider the scenario for each year, which is T. The population of forest trees represented by.
Oh, okay. All right. You can see I corrected the other one. So a student had come in early, and I'm going to make that correction right here.
Let me mute it.
I am muted?
Yeah, I'm sorry. My sister has a guest.
Okay, sorry.
And then my next question is, it's for number 3. It says using Excel, which is the forest population's growth rate at a faster rate, growing as a faster rate. Like I was able to calculate
Okay.
what the rates are, but like, what do you mean by putting it in Excel? Like, do you want us to graph it?
Yes.
Okay.
See. All right, so this is the question you're asking about, right?
Yes.
Okay.
So my question is, like, the 115,
it's not
is
in
there?
exponents.
Okay.
So I'm going to make that correction. I'm going to let the class know, okay? I just did the edit here.
Okay.
It's all in exponents,
Okay.
okay? All right, so now we are going to solve the other problem, problem number 5. Okay, you can see it says the population of a city is modeled by the equation P of T is equal to 256,114 times E to the power 0.25T. Okay, you can see that the T is in the exponent and using the exponential function, the exponential sign there. All right, so it's 256,114 times E to the power 0.25T. All right, so we're going to try to solve that. Okay, we're going to try to solve that. It says, if the city continues to grow at this rate, how many years will it take for the population to reach 1 million? Okay, so I'm going to stop share. I'm going to set up the problem. Okay, you can feel free to do what you want to do, but here we set up our f of t or our p of t. Equal to 2, 5, 6, 1, 1, 4 times E to the power 0.25 T, if I'm correct, all right? Now, when will P of T be 1 million? So here we say 1 million. Equal to 2 5 6 1 1 4 and P to the power 1 2 5 T. All right. Now, what we did the last time, we're going to divide by 256. One, 1, 4, and we'll divide by 256. 6, 1, 1, 4. So that cancels out. And what do we get here?
3.9045112723.
Okay. 3.119?
No, it's 3.904.
Okay, 904.
Mm-hmm.
Okay. I'm just going to take 3.904.
Okay.
Is equal to e to the power 0.25 t. All right. So now, again, we have the exponent here, but mathematically, if you take the log of each side, the log of e is 1. The log of e is 1. So if you take the log of e to the power 0.25t, you're going to get 0.25t, okay?
So the log of 3.904 is 0.591.
Yes. So you take 0.25t equals the log of 3.904. Okay. So what is the log of 3.904? So 0.25t equal to, what is the log of 3.904? Somebody tell me. Is
0.5915.
okay. The log of,
So then we're also going to use the log of 0.25.
no. Like I said,
No.
the log of e is 1. Because remember, you're going to take the log of this side and again the log of that side. But the log of e is 1. So it becomes 0.25t is equal to the log of 3.904. Okay.
So you got to do the log of both sides, you said?
Yes. And I'm using,
We can't hear you anymore.
okay, I'm doing the log to base 10, 3.904. Okay, I see the natural log here. Okay, natural log is 1.362. So the log of 3.904 is 1.362. One point 362. Now, remember we are raising to E, okay? So we're using E, so that means we are using what you call the natural log. So in your calculator, what you should use is the log that says ln, because we're using E. There are two kinds of logs. You have a log based to power 10 and a log based to power raised to the E, okay? There are two kinds of logs, okay? And this is why I say maybe we need to talk about that next week so that we can take time and explain the difference between the two logs, okay?
But
and why?
Professor, the
Yes.
log of 3.904, I got a different answer than 1.362.
Because you're using the log base to the power 10. You're using the log base to base 10. But you can see here we have E, okay? The log of E is what we call a natural log, and that is ln. That's what you should use.
Okay, I don't understand, but okay.
Okay, no, there are two kinds of logs. Did you get that?
Yes.
Okay, so log has a log to base 10, and there's also log to base E. Because the log to base E is ln, the natural log. And since we're using E here, then we're going to use the natural log. So the natural log here is 1.362.
Where is the E? Because you mean the T is the E?
No, the T is not the E. You can see here we have here E to the power 0.25. T, is that correct?
Yes.
Good.
Okay.
And because we're using E, we use the natural log, not the log to base 10. If you see where you say log, that is a log to base 10. Okay, log has two bases, and both of them will give you the same answer if you are using both on the same thing on both sides. Okay, but we're using E here, so we're using log to base E, which is called a natural log. Is that clear?
Honestly, I don't get it, but it's okay. You could keep moving. I'll try to figure this out later.
This is why I said let's have a different session and we go through that so that we can see the difference. Like I said, this is why I didn't want to get into it in the first place, because it's time consuming to explain logs, but it's not difficult to understand it. Okay, but it's just time consuming. But you need to understand the theoretical basis of the two. But because we're using E here, set that in your mind. Because we're using E here, use the natural log. You get it?
So the natural log is to the power of 10 or no?
You know, it's to the power of E.
Okay.
The natural log is based on E. The log to base 10 is based on 10. You get it?
Okay.
Okay. There are two different kinds of logs. So then here T is equal to 1.362. 2 divided by 0.25. So what does that give you?
I got 5.448.
That's correct. That is the correct answer. 5.448. So if you take 5.448 years, nearly 5 years, nearly 6 years, actually 5.5 years, not nearly 5 years. Nearly 5.5 years for the population to grow to 1 million. You get it?
Somewhat, yes. Thank you.
Okay. So essentially here we are solving for t instead of, if we are given t, then we can solve directly, but sometimes we are asked to find out t. And it's very, very important because sometimes you, like in a business decision, you ask yourself, how long would it take for my money to get to that point? And it says it's going to take 20 years. You say, well, I'm not going to wait 20 years. Okay. So what do I need to do for it to get to my objective in 4 years? What needs to happen for it to be there in 10 years or in 7 years? So these are the uses of this kind of calculation. So when we get to the time, to financial mathematics or the mathematics of finance, then we're going to do more of this. Nevertheless, if you really want to understand the theory of logs, then we just go back and work on it. All right?
Okay.
Okay. So any other questions?
Not here, no.
Okay. All right. So thanks for coming by, and so I'll see you guys next time.
Okay, Professor, have a good night. I'll give you a call tomorrow.
Sure.
Professor, I do have a personal question. So
Okay, so everybody else can leave, or you can call me back, and then I'll answer your question. Call me on my phone.
which
Okay,
number?
everybody's gone. I'll stop in for the benefit of the class. Okay, so you want to know what the BUS210 is about. Okay. Okay, so if you have like ax squared plus bx plus c equal to 0, right? Are you still there? Hello? Hello?
Yes, I'm right there. I'm listening.
Okay, good. This is the quadratic function. This is b, this is a. If I ask you to solve for x, we're asking you to find at what points this function is 0. What values of x are the function 0? Okay? But this function, let us just take an example of what this function could look like. This is y. This is x. This function goes up and down. These points here, 2 points that I mark, these are the points where the function y will become a 0, right? But this function here, what value of y, what value of s will give the maximum function? So this, I'm going to call it m. So for example, I'm going to use an arbitrary function here, not one that we're going to solve. Okay, 4x squared minus 20x plus 100. This is a function. It's an arbitrary function, okay? I'm not saying it is solvable. This is your A.
Yeah.
This is your B. And that is your C. Now, you can find the values of X where the function is a 0 here, where Y is a 0. So here, Y is 0. At this place I circled, Y is a 0. How about the maximum of the function? What is the maximum value of Y? What is the maximum value of Y? This is where you use minus 20 over 4 minus B over 2A, that is over 2 times 4. Okay? Like I said, this is an arbitrary function, so this is B this is equal to your B over 2A. You get it?
Yes, I do. I just don't know when, so
When I
B.
ask you to solve for X,
Mhm.
then you use minus B plus or minus the square root of,
Yeah, so I should use B minus B divided by 2/8. It was the right formula to use.
okay, so this is the formula if you want to solve for X,
Okay.
okay? Plus or minus. X is equal to, this formula gives you, this formula here gives you the max of Y. There are two different formulas. When you're looking for the max of Y, you use B over 2A. When you're solving for X, you're gonna get two values of X. You use this formula, minus B plus or minus the square root. Now, like I showed you here, let's go up. You see the maximum value of Y. There's only
Yeah.
one maximum.
Yes.
Good. So when you're solving for the maximum value of Y, you use B over 2A.
Okay.
You get it?
Yes, I do, because I was confused. I didn't understand which one to use or which not use. Okay then, so thank you.
All right.
All right.
Okay. Good night.
A good night. Thank you so much for your help.
All right. Bye.
Bye.